Assalamualaikum and very good day. My name is Muhammad Asif bin Muhammad Nazir. I am from class DET IAC 5B. So in this video, there are tasks that I will be completing with you guys for my subjects electronic instrumentations. Without further ado, let's go for the first exercise. So for the first task, our objective is to design a lab view to compare a simulated sensor signal with a threshold that a user defines using numeric and Boolean logic, and is to observe and analyze how the system triggers an alarm when the signal exceeds set limit. First, we take a while loop function from the programming palettes. Next, we add another function named simulate signal. Next, we need to adjust it to simulate a question timing. Next is we need to create a graph indicator for the sine wave. We also need to create the stop buttons for control for the loop condition terminal. Now, we need to go to the front panel. We need to click the numeric control palettes and select a vertical pointer slide. Next, we need to click the LED subtitle and place a round LED to the front panel. We need to set the vertical pointer slide on the properties, change the label to limit, and show digital display. And for the boolean LED, we need to change it to the alarms using the properties. Next, we need to double click the simulate signal to change the amplitude to 10. Then go to the comparisons, and for the comparison we need to choose the comparison functions and put in the block diagrams. For the comparisons we need to choose the greater and then compare to second input. Next, we need to reconnect all the block diagrams. Then we can run and test our systems. And that's all for exercise 1. For exercise 2, the focus point of this exercise is to configure a simulated NIDAC max device and acquire continuous analog input signal of a system using a lab view. It's also to calculate and display real-time statistical values, mean, maximum, and minimum from the acquired signal. So for the first steps, we need to open Measurement Automation Explorer. This is NIMAX. seconds. Under my systems tree, right click on the device and interface and select create new. Select simulated NIDAC max device or modular instrument. Choose device window, prompts that we need to select a device. Usually we text M series DAQ and select PCI 6221 in our NIDAC max simulated DAQ. After complete, right click on the PCI 6221 DAQ card and select test panel. Click analog input tabs and be sure we choose a def1 AI0 and select finite. Make sure the rate is set to 1000 Hz and sample to read is hundreds. After complete the sets, click start button. After it's all done, we can go to the LabVIEW software, create a new blank VI. At first, we need to take a while loop functions. Then place the accused assistance on the white loop. Setting the measurement, choose acquire signal. Measurement type analog input, voltage, channel def1 AI0. After all done, click finish. Another configuration window will appear. Change the task timing equation mode to continuous. Right click on terminal the EQ and create graph indicator. Place time delay on the palettes and type 0.1 for the time delay. Next, select statics and place it on block diagram. On the properties, make a selections for statistical calculation, arithmetic mean, extreme values, maximum and minimum. Right click on arithmetic mean, maximum and minimum and create numeric indicator. Switch to the front panel and rearrange our control. Save the file. Select write to measurement file from the express and output. Set the configurations and try run our systems. If the result shows, then your system is good to clear. For the third task, our focus is to implement a moving average filter in the LabVIEW Max script node and display the low, high input and output signal on the front panel graph. Then, it also to test the filter operation by setting breakpoints and using MaxScript probe to view intermediate variable and S1, S2 input signal, output signal to verify that high frequency content is attenuated. So for the first steps, we will use while loop with buttons functions. Then we will use MaxScript function and put in the while loop function. Then we need to write a code into the MaxScript functions. The codes need to involve filter length, flow for the lowest of two frequency components for input signal, and F high, highest of two frequency components for input signal. And also the output S1 equal to cos 2 times pi times F low times N, and S2 equal to cos 2 times pi times F high times N. And the input signal equal to S1 plus S2. Then we need to right click on the border of the MaxScript to add input and add output. Then we will write output signal equal to filter in bracket num1 input signal divided by m in the MaxScript. Then we will use breakpoint in the line of number 7 and number 10. We will right click on the border of the match scripts on the probe functions, and we will push step over each line of the script by pressing the step over line of script button on the toolbar. The result will show the data of our code. Next is for exercise number 4. Our objective for this exercise is to generate a simulated sine waveform and determine its frequency components by using the spectral measurements expressed VI. It's also focused on the generate and save an automated HTML report which includes both time domain, signal and spectral analysis results. So, for the first steps, we will use simulated signal functions, and we will configure the functions where we need to add noise amplitude 0.1 and integer number of cycle. Next, we will use spectral measurements, and for configure we will use a power spectrum and result in linear. We will connect the sine with the uniform output with simulate signal expressed to the signal input of the spectral measurement expressed VI. Then we will use the report express VI function from output subpalettes of the functions palette and place it on the block diagram. We will configure the data report as shown. Then we will connect the wire output of the EQ simulate signal express VI and the spectral measurement express VI to the inputs of the report express VI. For lastly, we will try to run the systems and check the results in file. Lastly, for the exercise 5, our main objective is to use the web publishing tool and LabVIEW web server to publish a LabVIEW VI as a web page. And it's also focused to access the VI remotely using web browser, request front panel access via web browser. So, for the first steps, we will use the VI from the access tool. Open the tools menu and select the web publishing tool. Then we will click the start web server. Then we will select our VI from a VI name. and configure the web publishing tool and click next. Click Save to Disk, then click Connect. To control the VI through the web browser, we will right-click on the front panel image and select Request Control of VI. And as for the result, we can control the waveform from the web page. Next, we go to the real-world engineering applications for all 5 exercises. For exercise 1, this type of threshold-based monitoring is used in industrial safety systems where sensor trigger alarms or shut down machine when values exceed safe limits. Exercise 2, continuous signal acquisitions and statistical monitoring are commonly used in factory condition monitoring system to ensure machine operate within safe performance ranges. Exercise 3, a moving average filter is widely used in sensor reprocessing, such as smoothing noisy temperature or pressure readings before they are used for decision making. Exercise 4, frequency domain analysis and automated reporting are essential in vibration diagnostics, where machines are analyzed for faults and reports are generated for maintenance teams. Exercise 5, remote VI publishing is used in remote monitoring systems, allowing engineers to control laboratory instrument or industrial equipment through a web browser anywhere on the network. For summary, all experiments demonstrate how LabVIEW can be used to build, test, and automate a real-world engineering system by means of signal generation in data acquisitions, processing, monitoring, and reporting, and finally, remote access. The first experiment illustrates how a real-time comparison and Boolean logic allow automated decisions, similar to how industrial alarms and safety controls works. The second experiment extends that by simulating continuous data acquisitions using NI-DAC-MX, analyzing live sensor signals and computing simple statistics. This reflects how real measurement systems are validated before using physical hardware. The third experiment is focused on signal processing, implementing a moving average filter in MaxScript to remove noise and observe time domain effects. It concerns the very common technique of sensor data smoothing and control system. The fourth experiment applies frequency domain analysis and automated HTML reporting on how LabVIEW can analyze signal characteristics and generate documentation for lag diagnostic or automated testing. Finally, the fifth experiment shows the capability of LabVIEW for remote access by publishing a VI to the web and allowing monitoring and control from any browser. This latter feature is essential in remote industrial operations, automated test setup, and distributed monitoring systems. That's all from me. Thank you.